Energy is very nice to work with within our problem solving when it is conserved. But there are times when the energy of a system changes because some sort of external force either brings energy into the system or takes energy out. So let's take a look at how that change in energy is calculated. In the simplest situation, a force is applied in the same direction as an object's motion. If the object moves through a distance of x, then the value of work is calculated by simply taking the force in newtons times the displacement x in meters. The units for work do turn out to be joules. We can see that by taking a look at the individual parts of it. Force would be in newtons, x, of course, would be in meters. But a newton is equal to a kilogram times a meter per second squared. We get that from Newton's law, Newton's second law. And so we can see here that our units would be kilogram meter squared per second squared, which is a joule. So our units for work are joules. And again, basic situation, we just multiply the force times the distance. But the direction that the force is applied is certainly important as well. So let's take a look at what happens in that case, because that will determine whether energy is being transferred into the system or whether it's being transferred out. If the force is being applied at some sort of an angle, either just because somebody is pushing on it, not horizontally, or maybe there's a rope attached to the object or something like that, in these cases, we need to use the component of the force that is parallel to the motion. And you can see from this picture here, you can kind of imagine the triangle, that the cosine would give us that component parallel to the motion of the block. Now, we've used a formula very similar to this before. We've looked at torque in the past, and torque is R times F times the sine of the angle. That is because torque dealt with the part of force that is perpendicular to the object, and so we were trying to make it rotate. In this case, if a force has a component with the object's motion, it does work on the object, meaning it transfers energy to the object or away from the object. We'll see that in a few minutes. All right, actually, we'll see it right now here. So when the force is directed somewhat in the direction of the motion, like in this picture A, then positive work is being done, meaning that energy is being given to the system. The energy of the object increases. But if the force somehow works against the object's motion, we consider that to be negative work, and that means that energy is being taken from the system. Again, make sure that you are really focusing on the idea that work is equal to the amount of energy that's being transferred. Okay, so work is energy, energy being transferred to or from the object. Now, a real common force that, of course, points against the object's motion is the force of friction. And so the work done by friction will always be negative. The object will lose energy due to friction. In that case, your angle is 180 degrees, and since the cosine of 180 is -1, that's where we get that idea that the work is negative. If the force is perpendicular to the motion, then there's no work being done. Now, that doesn't mean that the job isn't strenuous or isn't requiring a lot of effort on your part. If you stood there for a while holding, a 100-pound dog or something like that, certainly it's gonna require energy of you, but there's no energy being given to that dog, and so there's no work being done by your force. It's something really to think about because, again, we are not using the word work in the way that everyday people use the word work. Work is the amount of energy that is being transferred to or from an object, which I can't spell here. Transferred, there we go. An important force that is typically perpendicular to the motion is the normal force. It's not always perpendicular, but it very often is. And notice that that normal force never really contributes to the object's motion. It doesn't affect the object's motion, so it does no work. That's consistent with this idea of an angle being 90 degrees and zero work being done. Another situation where no work is done is when an object does not move at all. Okay, so for instance, here we have a situation where this person is holding a very heavy object, but because the object doesn't move, the no work is being done. Or here we have a couple of people pushing against each other. Now, again, they are both exerting forces, but because there is no displacement, if there's no motion of either one of them, then there's no work being done. Do keep in mind, too, that there are sometimes situations where there's going to be more than one force that's acting on an object, and so we may need to calculate what we would call the net work, where we add work, add energy for forces that help the motion, and then we subtract energy, have a negative work for for forces that work against the object's motion. All right, now this is the way that the formula sheet actually shows the work equation. It's going to look like this bottom example down here. So we're going to have to really make sure we understand this. This dot here is called the dot product, or it's a symbol of the dot product, and it tells us to take the two values that we're dealing with and then take the cosine of the angle between them. This is also written in integral form, and again, I know some of us are just sort of getting used to that. When your force is constant, then the force can be sort of pulled out of the integral, and we can think about work being just a constant force times dr, which just, again, ends up being our force times our displacement. A lot of times we're working in the x direction, so we just use x. And then again, that dot indicates that we need to make sure we include the cosine of the angle between them. We're going to see this in the later video that shows some examples, but when you're calculating work, it's going to be important to recognize where the object starts and where the object ends so that we can take into account the displacement of the object. FYI, we can also do this for rotational motion as well. So instead of work being a force times a linear displacement, we can talk about a torque times an angular displacement. Now, this isn't used very often, but if you come across it, remember that our linear formulas can always be sort of transformed into their angular forms. There's another video that shows some examples of how to do all of these calculations with these various ways of thinking about work. Make sure you check that out as well.